everyone, let's open up to lesson 11.5. So here for the do now, we are given three equations. Let's go ahead and calculate the change in enthalpy for each one of them. So for the first one, we have two options. So you can either go ahead and use the bond energies, or because we do have a shortcut available, which is table I, we can go ahead and check to see if this equation is on table I. So here's my table I, and I do see the equation for the combustion of glucose. The only problem is that the equation that I see in table I, which is, let me see if I can, okay, so this is the one that I'm talking about. So this is only for 1 mole of glucose. However, the equation that is given to us in the do now has 2 moles of glucose. So all that we have to do is multiply whatever delta H value we have, which is negative 2,804. So we're going to multiply that with 2. And that gives us about negative 5,608 kilojoules per mole. And by the way, this should be 12 oxygens here, not just 1. So same thing for equation number 2. We can either use the bond energies or check to see if this is on table I. So I have water that is splitting into oxygen and hydrogen. Let's see. So we do not see any water in the reactants. However, we do have this equation right here. So this is where hydrogen and oxygen are coming together to make water. So if we are looking at the reverse of this, then we are going to split this number. So we are going to reverse the sign of this number. The 571.6 will make that a positive number. And also, in the given equation in the question, we only have 1 mole of water. But in this equation, we have 2. So that means we're going to have to divide the 571.6 by 2. So delta H will be equal to positive 571.6 divided by 2, which gives us positive 285.8 kilojoules. And once again, remember, if you don't have access to table I, then you will have access to bond energies to answer these. For the third one, we have sodium hydroxide combining with hydrochloric acid, producing NaCl and water. Let's see if this is on table I. I just see splitting of sodium chloride and the splitting of sodium hydroxide. But that's it. No reaction of sodium hydroxide with hydrochloric acid. So let's see if we can use bond energies for this. So I'm going to focus on sodium because that's like a very niche element, not very common one in the reactants. So this is the table that I gave you for bond energies. And I do not see any sodium here. Interesting. So because for this question we don't have the bond energies, this is not on table I, so that gives us the aim for the lesson, which is how to calculate delta H without these two things. So we're going to do this without table I and the bond energies. So your answer is we are going to use something else, a different type of number, which is called the heat of formation. And in theory, this is the opposite of your bond energy. So bond energy is the amount of heat that is required to break a bond. So that amount of energy must be absorbed to break a bond. Heat of formation is the opposite. So this is the heat or the amount of heat released at 25 degrees Celsius and 1 atmosphere. when 1 mole of a substance forms. Meaning when we make one bond, then this is the amount of heat that is released. So table I includes the heat of reactions in general. So it has like a bunch of like different types of reactions. We have dissociation, we have combustion, but we also have some synthesis reactions. So it does give us some heats of formation. So let's look at some examples of the heat of formation that we can find in table I. So if, let's say, we are looking at the molecule carbon dioxide, let's go ahead and use table I to write down the equation or the heat of formation for the formation of carbon dioxide. So I do see carbon dioxide over here, and as we can see, we combine 1 mole of carbon and 1 mole of oxygen gas to produce carbon dioxide, and that requires, or that releases negative, actually when we say release, we don't necessarily have to say negative. So you can just say it releases 393.5 kilojoules of energy, or you can just say that the heat of formation in this case is negative 393.5. So let's go ahead and write that here. Now, when we are writing this in the equation, so carbon plus O2 gives us CO2. So gas, oxygen is a gas, and carbon is a solid. So if I want to write that 393.5 kilojoules is released, we are going to put that in the product side, because when something is released, it is part of the products, and if something is absorbed, it is part of the reactants. So this is my complete equation with the heat of formation or the heat of the reaction included. Next question is saying the heat of formation for NO is about 91.3 kilojoules per mole. What is this number? How does this number compare to the enthalpy value that is given on table I? So let's see. In table I, NO is right here. I have 2 moles of NO that are forming, and the energy is 182.6. So for 2 moles of NO, the heat of formation is 182.6 kilojoules. So that means this number right here is the half of that. So this is half of table I, because it makes sense, because this is only for 1 mole. So only for 1 mole. Next up, suppose I wanted to form a single monoatomic oxygen from the diatomic oxygen. So that means you start with the O2 and you split that into oxygen plus oxygen. And you are told that the heat of formation in this case is positive 249 kilojoules per mole. So because this is a positive number, we know that this amount of heat was absorbed because it's positive. So if we want to say that this heat was absorbed, we can go ahead and put that in the reactant. So I'm going to go ahead and put 249 kilojoules per mole in my reactants. So the standard enthalpy of formation for any element in its elemental form is 0, meaning if you are asked what is the enthalpy for O2, you're going to say 0. So why is that? Let's take a moment to think. So the answer is enthalpy depends on how much heat is absorbed or released during the formation of a substance. However, when we are talking about elements, they exist in nature like that. So we don't need any energy to form them. So elements occur in nature So no energy required to form them. And by the way, just to clarify a tiny thing, I know we said in the definition that heat of formation is in general the amount of heat released at 25 degrees Celsius and 1 atmosphere. But then you might be confused that why are you given a positive number here? In reality, when you are given the table with your heats of formation, they do look something like this. So as you can see, all of the numbers over here are negative numbers. There are very tiny cases when something might absorb energy, although in this case it makes sense why this is a positive number, because the bond is breaking and not forming. But there might be some very, very, very extremely rare situations where a whole bunch of bonds are breaking, but or maybe a whole bunch of bonds are forming, so like the net change is not the regular one. So in that case, I guess, just so you are not confused about this, we can go ahead and say or redefine heat of formation as the heat absorbed or released, just in case you do happen to see some of those examples anywhere. For example, in this table, the heat of formation for NO is positive 90.4, and then for NO2 they gave you positive 33.9. So just know that sometimes when there's other things involved in the reaction, or when we change the temperature and the pressure conditions, then things can change. Okay, so let's talk about how can we use these numbers if you are given the standard enthalpy. How can we use those numbers to predict or calculate the delta H? So super important. Remember that delta H equals the heat of products minus heat of reactants equation that we tweaked for the bond energy. Now, because heat of formations is the opposite of bond energy, so we can go ahead and use the same equation, the regular one, which is products minus reactants. So when calculating delta H using the heat of formations, then we can say delta H is equal to the heat of the products minus the heat of the reactants. So, and please don't forget that if we have any element, then their enthalpy is going to be 0. So heat of formation of elements is always going to be equal to 0 kilojoules per mole. So let's do that for the first one, and then I'm going to have you do the rest yourself. So you have 2CO plus O2 combining to make 2CO2, and our equation is delta H equals heat of products minus heat of reactants. So what I'm going to do is, let's write down the equation with the formulas first. So you have 2 carbon dioxide, so that means I need to multiply their enthalpies with the 2, minus you have 2 CO, so I'm going to multiply their enthalpies with 2, plus 1 oxygens. So let's go ahead and plug in the values for their enthalpies from this table that I gave you on the side. So for carbon dioxide, that is negative 393.5 minus you have 2 times negative 110.5 plus 0, because remember oxygen is in the elemental form right now, so there the enthalpy will be 0. So then you just go ahead and subtract these two, and that gives you your answer. So go ahead and make sure you have completed 2, 3, and 4 before you come to class tomorrow, and I will see you in the next one.